Hello everyone, my name is Ömer and now I'm going to present my EE474 term project um, investigation of MRI RF pulses. So what is RF pulse? RF pulse is mainly the tool to excite the body. It is the main reason that's causing the resonance of water molecules. Therefore, it can be used to excite and image any voxels of interest. And to be more specific about the technical part of the RF pulse, there are two main reasons of their usage. One is to create the selective excitation process, where we can image the slice and select the slice that we want to image. And secondly, to create the flip angles, the amount of rotation that the initial magnetization will eventually rotate. Um, Why do we have to design RF pulses? There are many various techniques and sequences to obtain an image, and in order to maintain those sequences, we need different tip angles and different kinds of RF pulses. Therefore, we eventually need to have some specific design criterion for this RF pulses. For example, this fast spin echo sequence could be shown like the first initial RF pulse has to be 90 degrees, and the following consecutive pulses have to be 180 degrees to obtain the image. And similarly, in multi-slice excitation, there has to be different frequencies for each slice value. Therefore, within one um, image recording, we can obtain different slice selections with different RF pulses with different frequencies. Therefore, the design becomes pretty important. There are, um, to be a bit general, there are mainly four different points that one should consider during this design phase. These are the frequency, amplitude, duration, and the shape of the RF pulse. There are many different techniques to design RF pulses, but the most common and perhaps easy to use one is multi-angle approximation. To be more advanced, one can prefer to use Schneider-Leroux technique, or there are many different detailed optimization techniques such as Bloch-Siegert's B1 mapping and RF optimization. But these Schneider-Leroux and Bloch-Siegert is a bit more out of the scope of this course. Therefore, I'm not going to make an introduction to them. And for small tip angle, this technique is useful when the tip angle is below 30 degrees. However, if it's not, still it's a good approximation. There are two main properties that should be considered for great intuition. First of all, if there is a refocusing in the gradients, then the Fourier transform of the impulse becomes the slice excitation profile. Therefore, we can design the pulse so that our target slice could be excited. And also, the area under the curve of the RF pulse could be approximated as the flip angle. Therefore, it's pretty useful when trying to calculate things with some small minor errors due to this approximation. In order to explain those different RF pulse design techniques and properties of the RF pulse, I've created some sort of a little playground for these signals and their effects. And I've tested some common signals such as square waves and Hamming windowed sinks. And as the arbitrary single, I've decided to try a cosine just to see how things would work out. These are the results of the square wave. As it could be seen, there is a little square wave applied on the left, and its Fourier transform shows how the slice excitation works. As it's known, the rectangular pulses Fourier transform is a sinc, and due to this property, there are excitations on the outside of our main interest, and this might eventually cause some very minor errors. And since there is a clear area under the curve in positive x direction, the magnetization vectors tip towards the x direction. And for the windowed sinc, the pulse is represented on the left and its Fourier transform is represented on the right, even though it's not strictly a rectangular pulse. It's due to the sampling property problems in MATLAB. But it's way clearer than the rectangular pulse, as we have seen before. And due to the similar reasons, due to the area under the curve being positive, the magnetization vectors are tipped towards x direction, and we can see that the tipping is less than the first pulse due to the area under the curve being less than the rectangular pulse case. And for my arbitrary cosine example, there's an interesting RF pulse there, and since this is a cosine, we have an like a slightly useless Fourier relation here. We can see that the middle part is less excited than the outer parts of the voxel. Therefore, this might cause some perhaps amplitude problems in this excited imaging process. Therefore, cosine wouldn't be the first choice that would be wanted to select it. And for the magnetization vectors, since the area under the curve is now negative, then the tipping direction is towards the x direction, and in the reverse direction that previous pulses were making those vectors be rotated. And now there will be a little bit of a demo for 2 or more RF pulses. And this photo represents the movement of the first excitation and the second rotation due to the second excitation. Also, at this point, we can first check the first playground part of the project. We can select any pulse that we want to test. For example, we can test the sinc example that I have shown in my PowerPoint slide. When we enter this pulse, we can see how the what kind of shape this RF pulse has, its Fourier relation, and the change in magnetization vectors. And this could be exemplified with any kind of pulses. For example, I can try some sort of a new rectangle, such as, let's see, like this one, and we can change the amplitude to increase the tip angle. And now we can see what kind of a RF pulse we have applied here, and we have seen its change in the Fourier relation. And since we have increased the duration, now we have a better approximation here. And now we can see it's obviously the tip angle is way larger than it was before. And we can play with this parts with any pulse that we want to try. And for the second part, we can apply different pulses, such as we can apply 90 degrees in X direction to start with. And we can see how this changes the RF pulse. And for the second part, we can apply another 90 degrees in Z direction, so that we can have such sort of movement in magnetization vectors. I just plot these vectors on top of each other to like show the history of the rotation. It's a bit more clear this way. Or we can try any different combinations, such as we can apply 90 degree in X direction, and we can try 180 in Z direction, and this is a commonly used sequence, since it's pretty common to use spin echoes or fast spin echoes and those kind of inversion processes. The direction of these pulses could be changed from the code, but it's just to demonstrate how this works, so I haven't changed it a lot. And this is mainly my playground and my project, so thank you for listening.